T, you can write it as the range of T, range of the linear transformation plus the kernel of the adjoint. But since the orthogonal projection is always self-adjoint, so it should be equal to the range of T. Okay? So this is something that you get as an outcome actually. Okay? Now let's take, for example, a matrix, and let's create an orthogonal projection, and let's see that whether it is an orthogonal projection or not actually. So here's an example. So let's take V to be R2 and consider a matrix A. Okay? So it's -1, 1, -2, 2 actually. Okay? So the operator, projection operator now is going to be the operator that is induced by this matrix. So let's call it PA. That is going to be vector from R2 to R2. And how does it going to look like? So P operated onto some XY is going to be this matrix multiplied with XY. So it's going to be -x minus 2y. Okay. This row, no. This row and the column. So -x plus y and -2x plus 2y. So this is transformation. The question is this P an orthogonal projection? The answer is yes actually. I mean, what you can check easily. Indeed it is self-adjoint because its conjugate transpose is equal to itself. So 8. Okay. So since A square is equal to A square is equal to A, so the P must be idempotent because P operated onto V is going to be really what do you call AV, and AV is really A square V, and A square V means A multiplied by AV, and if this is the case, this is same as A multiplied by PV, and then this is same as P operated onto PV, and therefore it's the P square V. So this shows that P is what do you call idempotent. So P is also self-adjoint because if you compute, for example, P star V, so it's going to be A star V, okay, and A star, the conjugate transpose of this is equal to itself. So it's going to be what? So it's going to be this matrix -1, 1 and -2 and 2 operated onto say vector V. Okay, shows that this is not equal to AV. So this is not equal to PV. So this means that P star is not orthogonal projection actually. P is not orthogonal projection. P is not orthogonal projection. Why? Because it is idempotent indeed, but it's not self-adjoint actually. So hence you're going to say that it's